Well, welcome to all of you. I was thinking about the
Morning,
delay
sir.
morning. Oh, my daughter Julia Kashopi. Haha, I'm happy to see you. Good to know that you are present to today's class and that you will make the most of it. Great. Let me share the screen. All right. Once again, good morning to all of you, and welcome to this third edition of our Numerical Method 2 class. Last time, we had the MATLAB practical session where we solved this problem. We fitted this function to a set of data points given in the form of a table. So that's what we did. We used MATLAB. We used the backslash function. And if you recall well, I said that the MATLAB backslash function can also solve overdetermined or underdetermined linear system. That is least square method. So under the symbol of the backslash, there are many hidden algorithms. It's not just a single algorithm, but there are many. So that backslash function can optimize, meaning depending on the nature or the shape of the coefficient matrix A, it will select the appropriate algorithm to solve the corresponding problem. Yeah, so that's what you need to know about the MATLAB backslash operator, because it's an operator. So I promised that today we will do something similar using Python, if I'm not mistaken. I think that's what I said. And I asked you to try to research about that, or to do it yourself, to be proactive, right? And I also promised that you'll be solving the normal equation for integral. I asked you to try to solve to make sure that you get the coefficient, the general coefficient when you solve the least square problem for discrete point, because integral means that your points are continuous, not discrete. This is the homework that I gave you. I say use this minimization problem and this is the optimality condition. So for an arbitrary j, differentiate this expression 112 with respect to a sub j. And if you do that, you should actually get this form. So this is what I asked you to do as a homework. I hope you did it. You have to be able to get this formula. You have to. Okay. So I promise that we will do it together for the continuous case. This one. This one. This is a continuous case. Because you can see that here we don't have a set of data points, but we have an entire interval, AB. You see? So that's why instead of summing, we integrate. because x is no longer discrete, but it's continuous. And for that purpose, we use the integral, and our normal equation, our minimization problem becomes the minimization of this error. And if we perform this optimality condition, we differentiate this related to a certain a sub j, where j is fixed, we obtain this expression. So this is our normal equation, because if we set this equal to 0, we can write this as a linear system, and we obtain this. And I promise that is the agenda of today's lecture, or today's class. Now, if you cover this, we are done with the section pertaining to the least square method. Right. Okay, so let us start. Okay, I think the one that will be easy will be to stop this information. This one. Okay, so what I will do, I will copy this. First of all, okay, so let me obtain this. So I will copy this expression, and then I will expand it, because remember that this is the sum of the difference of two expressions. You have f of x, and you have this summation square. So we can expand this, right? So I will start. I'll start with that one. So let me write this expression on a piece of paper. So E sub A0, A1 up to AN is equal to the integral from A to B of the error term f of x minus Pn, where Pn is this sum, k running from 0 to n, aka x to the k. So this is our Pnx, and that is squared, because that's the least square method. So this is 117. All right, now let me share the screen. Okay, so I will open. Okay, so we have our new window there. Okay, so this is what we did last time. Okay, I will just continue here. Right, so today's date is the 20th. Let me just write 20th here. Right. Okay, so what we want to minimize.
Sir,
Yes.
I can't see your screen.
Who can see my screen? Oh, yes, you are right. Now it's not highlighted. I don't know what happened. Let me share it again. Yeah, sorry for that. I can see that it's not shared. Oh. Okay. Okay, you can see it now, right?
Yes, sir, I can see it now.
Great. So as I said, we are minimizing this expression. And what is that expression? Since we are in the continuous case, no longer discrete, we integrate all over the range or the interval AB. So the error is f of x minus Pnx. And what is Pnx? Pnx is this summation k running from 0 to n, because it's an n-degree polynomial. So the general form of an n-degree polynomial is x sub k x to the k. And that is squared because it's the least square. So we square that error. And this is our equation 117 in the notes. Good. All right, so we first expand this. So this is the minimum. We minimize over the a's. So we minimize. So we are looking for the a's that will minimize this expression. Minimum. Good. So what is this expression? E. E. So we can rewrite E as. So you can see that this is like f of x is our a. So we can label this by a, and all this is b, right? So what we have here, of course, these are functions of x, right? Okay, let's call that ax if you want to indicate that it depends on x, because we are integrating. Okay, there is dx here. We are integrating with respect to that. So we are integrating ax minus bx squared dx. But don't forget this identity. We know that if I have a minus b squared, this identity, if you recall, from first year, I've been emphasizing that this formula should be known. This is an identity. In fact, maybe some of you have done that in high school. So I did this in high school. So the formula, each time I write it, is a reminiscence of my high school. So this is a squared minus 2ab plus b squared. So the factor of the squares are positive. You have positive, positive. And now the cross factor, the cross product here, when it's a difference under the square, the cross product here is negative. So negative 2 times, right? Here. So you see 2 here square, you have 2 here again square, but now this 2 is now a factor of the product A and B. It's really easy to remember. Since high school, I've been remembering this formula. I don't memorize. Good. So we'll apply exactly the same thing to this. Okay, let me now denote this by equation 1 for the present slide. Because here I call 117, that's with respect to the notes. But now for my slide, I call this equation 1. I hope there's no equation 1. Okay, there's no equation 1 there above. Okay, so if I apply this to equation 1, so this will imply that my E will be equal to what? I just expand this so I can read this directly and substitute the values, right? So I do that and I integrate at the same time, because remember, integral is linear. So if I integrate this expression, it will be integral of this minus 2 the integral of that, integral of this. So I have 3 integrals if I expand this expression and integrate. So I can do that right away. So the first one, A, is this one, f of x squared. So that will be that. So I have the integral from A to B, f of x squared, right? I can put a square here, or I can write whatever I want, but squared. dx for this first expression, right? Now, minus 2 times the product, so that would be minus 2 times. I can take it out of the integral sign because it doesn't depend on x. And then I integrate from A to B. The product, that is this product, AB. All right. Which I can still, if I want, because this doesn't depend on the sum, I can even take it inside. But anyway, it doesn't really matter the order in which I'm writing this. Yeah, I can take the sum, right? Because this summation depends only on k, so I can take even, okay, but let us write it like that for now. AKX dx. See, in this factor like that. dx. And finally, b plus b squared, which is this squared, this entire expression squared, plus the integral from A to B, the entire expression squared. So that's what we get at this stage. But if you want, we can still even take this, everything that does not depend on on x, I can take it out of the integral sign. But here I cannot do that at this stage because of the square, except I expand this also, then I could take the summation out, because the sum does not depend on x, so I can take it out if I expand this expression. Okay, so I can write this is equal to the integral from A to B f of x squared dx. Now you see that this doesn't depend on the a's, right? On this coefficient, because remember, we will differentiate with respect to the a's. So if I differentiate this with respect to a, this is 0, because it doesn't depend on a, right? When we differentiate. Okay, so now this expression I can write minus 2 times summation. So I can take this summation with the a sub k, because a sub k does not depend on x. So I can take that out of the integral sign. So under the integral, I will have this product, f of x, x to the k, or x to the k f of x. It doesn't matter. Right, so I can write this fx dx for this expression, right? Because I can take this summation, integral being linear. I can take f of x under the sum, because it does not depend on k, so I can multiply throughout. And then because this ak and the sum depend only on k, not on x, I can take that out of the integral sign and get this expression. Right, okay, plus I can write this part plus this last term plus the integral from a to b, this summation over k, ak x to the k dx. Right. Now, if you look at the expression, let me write this first before I share the screen for you to look at the expression in the notes, right? To see if we have a similar expression, which should be the case. Maybe they might be written differently, but we should have the exact same expression. Okay, so after that, the next stage will just be to differentiate this expression with respect to a fixed AJ, A sub J.
Sir,
Yes, you have something to say? Yes?
sir, what's the square on the last equation?
Oh, yeah, you are right. Thank you so much. Good. Great. So now let me share the previous slide again. Okay. Now, if I share the previous slide again, oh, today Simeon is present, which is not bad. She was absent. Now, if you look at this, you can see that the first one is this exactly. We have exactly this one, f of the integral of f of x squared dx, and we have this minus 2 summation ak, and then the integral, and out under the integrand is x to the k f of x dx. That's exactly what we have. We have in our on the slide, on the other slide, right? Okay. And this one squared. You remember you said I should put a square. That is exactly what you have there. So we have the exact same expression. So what we have done here is just simple expansion and arrangement of terms. So there's no magic here. We did not do anything good so far. This is elementary. So even a high school learner who knows a bit how to manipulate this thing, he can do it, right? Okay. Oh, what is happening with this thing? It's making noise. Okay, so we are done with this one. Now let us differentiate. Let us fix J, right? We fix it because you can see here in the summation, it depends on K, right? Now we fix J, an arbitrary element between 0 and n, right? Because K here varies, and K can take any value between 0 and n. So we fix one of them, and we call that J. Is that understood? So we fix, I hope you understand what I'm saying.
Not really.
Not really. Okay, I will explain. You will understand really. Okay. I will explain what I mean by that. You know, this is mathematics, it's not witchcraft, it's not it is not literature, it is not mahangu. Oh, some people ate mahangu during the break. Wow! And some of you have become fatty boom boom because of mahangu. It was so nice that you didn't want to leave it. All right. This is what I mean. Okay, let me go to the next slide. Next. Yeah, This is what I mean. When you look at this summation, this expression, this one or that one, I can write this, right? I can write this. Okay. Example. If I write here example, is to illustrate what I'm talking about here. Example. I will call this Lx, this one, this expression. I will just take the middle part, this one, the middle term. So this middle term, let me denote that by Lx. You see, this depends on x, it doesn't depend on k, because k varies. If you expand this, you will not see k, right? If you expand this, you will not see k. You only see, I hope you understand what I mean. Okay, so this is our Lx. I can write Lx as, now if k is equal to 0, so there's no negative. When I say Lx is from 2, I forget about this negative sign, so I take from here. You see that this does not contain the negative, it's from 2 up to there. Now, if I expand this, you will see that this expression does not depend on k. K is just a variable. It does not. If I expand this, you will see that k equal to 0, I have a0 to a0 to a0 integral from a to b x to the 0, which is 1. Okay, then I have f of x dx. You see, this is what I have. Plus, when k is equal to 1, I have 2a1. Same thing, integral. Now with x here, f of x dx. Up to the last term, which is 2an, the integral, so this is an, x to the n, f of s dx. Now you can see that this is not dependent on k. That's what I was saying. K is a variable. So if you expand, you don't see k in this expression. You see a0, a1 up to an. You don't see k in this expression. Okay, now you can see that now, since I want to differentiate, let's say this term with respect to one of these terms, my j can be 0, it can be 1, it can be 2, 3, 4, up to n. It can be any of them. That's why I fix it. So I can say, for instance, if j is equal to 1, I differentiate with respect to a1. If j is 0, I differentiate with respect to a0. If it's 5, I differentiate with respect to a5. If k is equal to n, I differentiate with respect to an. You understand now? I cannot differentiate with respect to ak because ak does not mean anything. It's just a variable that takes any value from 0 to n. But actually, if I want to differentiate with respect to one of the a, I have to fix the j between 0 and n, and I differentiate with respect to that j. For instance, if I want to differentiate with respect to a1, you can see that this is my a1, the coefficient, and these are the factors. So if I differentiate with respect to a1, you see that it will give me 2 integral from a to b x f x dx. If I differentiate with respect to an, where in this case my j equal to n, here j is equal to 1. Now this will be equal to what? It will be 2 integral from a to b x to the n f of x dx. That's what it means. So my variable like x is as if you have, let's say y. You can call this y. You have y here in place of a, and you differentiate with respect to y. Because there's no y here, any other term is considered to be a constant, and then you get that term. You understand now why, when we differentiate, we say we differentiate not with respect to k, because k does not mean anything, it's just a variable. We differentiate with respect to one of the terms which we denote by j. That's exactly what this means. So we are going to do that. So I fix j between I hope this is clear. If this is clear, then the rest is easy. So we fix J between 0 and n. So it can be 0, it can be 1, it can be anything as I did here. When we fix one of them. Now we are going to differentiate E with respect to AJ. Now, if I ask you what is the partial derivative of this with respect to AJ, you will say that is what? It will be 2 integral from A to B, x to the j, f of x dx. Right, that's exactly what you will say. Okay, now let us come to this expression. So now, if we differentiate this with respect to a fixed j, which is any value between 0 and n, you can see that this does not depend on a. Okay, another the best way for you to see, let me do this for you to see properly. Let me do this, otherwise you will not get it. Let me rewrite this expression with respect to j, this fixed j. I can write it this way. I can write a e a0 up to an. In terms of j, I can say that it is equal to, okay, this is a constant term, it's still there, f of x dx, that is f of x squared. Okay, now the middle term minus the middle term, which is our lx, what I call lx there. Now, if I expand that with respect to aj, I will write it as 2 times aj, because I just take k equal to j, right? So that would be aj, the integral from a to b, x to the j, fx dx, right? Now, the remaining terms will be all the terms present in the summation except j. So the remaining term will be minus 2 summation. Minus 2. We have now the summation here. K running from 0 to n, but this k will skip j. So I will say k not equal to j. So if there are, let's say, 10 terms in the summation, if I isolate aj, then in this summation we'll be left with 9 terms. So in this summation, instead of n plus 1 term, because we start from 0 to n, which is in total n plus 1, it will be only n terms because I will isolate the value k equal to j. So I can split this sum into 2, the term that I want and the term that is not present, because I split the summation into 2. So this is what we have now. So this will be a k, the integral from a to b, x k f of x dx. I hope this is clear now. And similarly, for the remaining term, this one in this integral, this one, I can do the same thing. I can write that it's the integral from a to b. Then I can write my expansion here. I can say that this is a j x j plus the sum where k takes all the values but except j. I could have written like this, but I can just say k different from j, but it takes all the other values. ak x to the k, and we square all of these dx. Now, if I want, I can call this a and this b and do the same expansion as we did, but I don't need to do that, right? I can apply my chain rules here directly, and I will still get what I want. Okay, now let's differentiate this. Now, if I differentiate with respect to this fixed j, if I differentiate this with respect to my fixed aj, you agree with me that this one does not depend. So if I differentiate, it will be 0. Now, this one, this is my variable aj. This is a constant term. So if I differentiate this with respect to aj, then I will be left with -2, that integral. So minus 2 integral from a to b xj f of x dx. So that's what I get from differentiating this term. Now, if I differentiate this, my aj is not there. I have all the k has all the other values from 0 to n except the value j. So if I differentiate with respect to aj, it will be 0 because a sub j is not present. So a sub j does not appear in this term. So if I differentiate with respect to aj, this will be 0. Good. Now I come to this term, I apply my chain rule. I can differentiate under the integral sign because this integral does not depend on aj. So I can take the derivative inside the integral. So now this is a chain rule. The chain rule, if I apply the chain rule to this will give me plus. Now I differentiate this chain rule, so this comes down, so it will be 2 integral from a to b, this term, because the power will be reduced by 1, right? So this will be this entire summation, right? It will be this entire summation, which I can write sum j running k running from 0 to n, k running from 0 to n, ak x to the k. So because I'm not differentiating what is inside, but I'm applying the chain rule. So I first lower the power, so the coefficient, this 2 comes down, and then I decrease the exponent by 1. So that's what I've done here. I don't touch what is inside. So that's why I still have all this summation. Now, when I differentiate the inner term, which will multiply this one, you can see now if I differentiate the inner term, this expression does not contain aj. So when I will differentiate this inner term, this will be 0. Now, if I differentiate this first term with respect to aj, then I will be left with x to the k. Oh no, sorry, this is x to the j, sorry. Because k is equal to j. Nobody told me that this was a mistake. Not even Kashufi. So this is j. So now if I differentiate this with respect to aj, I'm left with x to the j. So you can see that. So this is x to the j. dx. Now you can see that since this depends on x, because this is the power of x, so it depends on x, I cannot take it out. Now I can still multiply inside, right? Because this xj is a factor of all these terms, so I can multiply throughout and increment this. So this will be equal to -2 integral from a to b x to the j f of x dx plus 2. Okay, now if I take this inside, this factor will be x to the k plus j or j plus k. Now I can take the term that do not depends on k. So I can take this summation k running from 0 to n ak. I can take it out of the integral sign. So if I do that, I'll get this summation k running from 0 to n.
So
Yes, ak. And then integral from a to b x to the k plus j dx. So this is what we get. Obviously, I just explained, that's why I'm writing this, but I explain what I've done here. I first take this factor inside. Right. If I take this factor inside, this will be, that is xk times xj will be x k plus j. That's what I will get under the sum. And then by linearity, I can take this sum out. And because ak does not depend on x, I can also take that out. Then I will be left with this. Right, so that's what I did here. I hope it's clear for everybody. Okay, so this is the final result that we have. Now let us compare with what is in the node to see if we don't make any mistake. So if everything is fine, if we did not make a mistake, this is what we should get. This is what we should get. Okay, what else? Even this x to the k, no, I cannot take it out because it depends on x. Okay, so I cannot take anything here out of the integral sign. They all depend on x, so I keep them there. So let's look at the slide. Let's look at the slide to see if our result is correct. Right? Let me first copy the result there so that we can compare. So 2 times summation k running from 0 to n ak into the integral from a to b x to the k plus j or j plus k dx. Okay, so now let me share. Let me share this the slide again. So we have this. Yes, this is there. Plus 2. Exactly. Wow. Ha ha ha. So this is not witchcraft, guys. You can see that we obtain exactly this. I'm sure if I gave this to you as an assignment, some of you can be locked in a room after 100 years. You come back and find you there. You did not even move. Oh, anyway, I'm just particularly those who like Mahangu too much, man. You'll be thinking about your Mahangu. Don't disturb me. Bring me my Mahangu. I want to eat my Mahangu. Don't disturb me. Okay, so that is it. You can see that we got the result, which is nice. Now, if you let this to be equal to 0, you just take the non-term, which is this one, to the right-hand side, and we divide by 2. And we finally get this normal equation. Right. Okay, so that is it. It's really easy. It's really easy. Yeah? It's easier than to eat Mahangu. You can see it by yourself. Okay. So you have done the most difficult part by eating Mahangu, because to cook Mahangu, you have to do this, you have to do that. Oh, it's a lot of work. But here, this one is really easy. The time somebody's cooking Mahangu, you are done. You are done with all your computations. So now, if I enforce that this is 0, you can see that I can take this. Of course, I divide the entire expression by 2, right? And I take this to the left-hand side. So if I take this to the left-hand side, this will imply we have this expression, the sum ak, the integral from a to b. Some people are still puzzled that how come we got this result. I already explained, you should not be puzzled. Everything is easy, it's just easy. Equal to, so I take this to the other side, is 2 here, 2 there, I divide, cancel out. Then we have our integral from a to b, x to the j, f of x, dx. Okay, as I said already, you have 2 here, you have 2 there, you divide, so you cancel that out to get this expression. And this is true for an arbitrary you can see that we fix j. So j is any arbitrary number between 0 and n. So this expression now is true for j. Since it's for an arbitrary j, I can say it's for j, taking any value from 0, 1 up to n. So for each j, I have an equation. So in total, we have n plus 1 equation. And how many unknown do we have here? How many k do we have here? N plus 1. So you see that it gives us a linear system of n equation in n unknowns. And if you look properly, this is a function of what? This is a function of j. This one depends on j. So I can call this entire expression. Okay, this is my unknown. Okay, what I mean is that this is a linear system. A linear system can be written in this form. You have your coefficient, which are this one, and you have your unknown. Our unknown is this one. Even though we call it AK, but this is our x, if you want to call it x. Like x1, x2, whatsoever. And these are the coefficient a something, but I can call it b. So I can say it's something like, okay, let's say our coefficient, we call it c. So let's call this c. If I integrate with respect to x, it will depend on okay, this what varies is this one. It depends on these two, k and j. So I can call this, okay, since it's the coefficient, I will put it here. I will say c. This one is c, kj or jk, it doesn't matter. It's symmetric. So we have j, comma k, and this one is our unknown, like x, but I will call it ak or x sub k. This is our unknown. Okay, okay, x is already here. It might confuse, but that's not a problem because we integrate with respect to that. But for you to understand, let me put it in the form that you understand. So I can say that from 0 to n, and this is x. This is something like xk equal to, now if I integrate this, it will not depend on x, right? If I integrate with respect to x, it will only depend on j. So this is like our b sub j. If you recall the way we write linear system, we usually write it as a I j x of the other variable, because if this depends on j, it means that we sum with respect to I, right? So this is summation I running maybe from 1 to n or whatsoever, 0 to n, whatsoever. Here we have the variable, and we have we sum with respect to, sorry, I say with respect to I, sum with respect to I here, and then we have ij, and this is xj. xi, sorry, because it's invariant. Now you can see that j here is fixed. It's some related to I, so whatever is there will depend on that j, b, j. This is exactly what you write in the form of ax equal to b. You see, this is a linear system. That's just what I want you to see. That this expression gives us a linear system in this coefficient, and the unknown is this, our x, or in our case, our x, the variable, or the unknowns are the a sub k. These are our unknowns. So if you write it as a linear system, this is how you should identify this is a linear system, right? Okay, this explanation is just for you to identify that it's actually a linear system in the unknown x, which is our AKs. Our AKs are the unknowns, and the coefficients are these integrals. These are our coefficients. They are known. I know this term. Right. Okay, so that is it for that. Oh, unfortunately, it's already it's time. We'll stop here, but it was worth it to go through all these steps for you to understand, because I'm sure if I just left you to do all the calculation, most of you would have really found it difficult. So that's why I took time to do the derivation. Please go and do that all over again, and do the same thing for the summation, for the discrete case, because what I've done here is for the integral. Please go back and do the one that I asked you to do as a homework. With this explanation, you'll be able to do that on your own. I hope you are happy with what we did today. Anyway, if you're not happy, I enjoy it myself. I hope Kashopi also enjoy with me. Okay, guys, thank you for your kind attention. We will stop here for today. God bless you, and see you next week, Monday. Bye-bye.
Bye.
Bye.